Thank you for tuning in to Stay Sharp with Razorleaf, your secret weapon for all things digital and manufacturing. In this episode, Jonathan and Jen are joined by Ron Fritz, the CEO of TechSoft 3D, a well-known provider of engineering toolkits that establish the building blocks that developers depend on to give their applications more 3D power. It's all under the hood, so if you are in digital manufacturing, you have likely benefited from their technology. In this episode, Ron shares his unique perspective on the digital manufacturing space, where it's been and where it's going. The conversation covered the basics of platform evolution with Windows and Mac, to cloud and mobile apps, gaming, and even standards, or the lack thereof, in the industry. Join in and listen to Ron and our Razorleaf team as they take a look back together.
Welcome back to Stay Sharp, where we discuss all things digital related to technology, products, and manufacturing. I am joined again with my colleague, Jonathan Scott.
Hi, everybody.
In the digital innovation space, we spend a lot of our time focused on moving forward. What's next? Where do we go from here? How fast can we get here? Every once in a while, it's good to kind of take time to pause and reflect back on some of the changes we've seen and how far we've come. Joining us today to do just that is another industry veteran, a good friend of mine, and in fact, a past boss. Ron Fritz is the CEO of TechSoft 3D. And while you may not have heard of TechSoft, they have been helping engineering software teams build great products for over 24 years, which has given Ron a kind of a unique perspective on digital transformation. If you've been in the digital manufacturing space for more than a couple years, I can almost guarantee that you've utilized their technology in one form or another. So Ron, before we get started, can you give our listeners a little bit more background on yourself and TechSoft?
Thanks a lot. Thanks for having me, Jen, and nice to meet you, Jonathan. Well, I think you recapped it fairly well, but yeah, I was one of the co-founders of TechSoft 3D 27 years ago, and what the company does is provide the building blocks that the developers whose names you know well, SolidWorks, Autodesk, PTC, Ansys, Aris, on, depend upon to give their applications more 3D power. So our technology is under the hood in a lot of the millions of seats of software that get used by engineers and architects and builders every day. And now there's several hundred, close to 700 companies that depend on us as a strategic technology partner, even though you probably never heard of us.
Kind of like BASF. We don't make the products you make, but we make the products you make better.
We make the 3D you experience just that bit better.
Well, like you said, we've been looking at over the last 25 years or so, platforms have changed significantly. When many of us started, the various flavors of Unix were prevalent, and Windows was the big newcomer on the block. Since then, Unix has been eclipsed by Windows, Mac OS, even Linux, mobile platforms, et cetera. How has that changed some of the products that you have seen? How has that changed TechSoft and what you provide to folks?
Well, it's made our lives a lot easier. I'll say that. Having supported lots of the flavors of Unix in the past, this has allowed us to focus in on supporting Windows, Linux, and Mac OS. Saved us a lot of engineering time. And it's not just us. When you kind of zero in on those platforms, everybody gets to use their engineering time for value add instead of supporting a lot of different formats. At this point, by far, what we see from the companies using our tools, Windows is the gorilla for sure. In terms of desktop applications, Linux has found its spot, servers, and so we certainly see a lot of that. I've been surprised I haven't seen more Mac OS. With so many people using Macs and their powerful capabilities, we don't get nearly as much push for supporting Mac OS, although we do.
And that's interesting. So it's less, I don't know if variety is the word I want to use, but diversity in terms of platforms now than it was back in the days when we had so many Unix flavors. I was thinking that Linux was going to make it about the same, but no, it's actually simpler now.
Yeah, we would have predicted actually at the time that Linux and Windows would really battle it out. We committed a lot to marketing to the Linux community, but in terms of professional grade engineering software on the desktop, it's Windows by a mile.
One of the other platforms, of course, that has come up is really mobile. And it's, I know that, when we had started working with like e-drawings, for instance, on mobile, that was, I think, one of the first ones that was introduced on that platform. Do you ever see it becoming a big platform for 3D?
I actually am surprised it's not as big as it it's not as big as I would have guessed, actually. Let's say, 20 years ago, I can remember being at a DARTech conference and showing 3D on a Windows CE device and people being blown away. And I thought, this is it. Everything's going to be mobile. It's not. There certainly are very nice applications on mobile platforms like Shaper 3D in the design and creation and others, and then consumption applications like e-drawings. But we haven't really seen the big uptick. But I still have faith that we will see a lot more 3D on mobile because of XR. And there's people, those glasses have not taken off and they may not take off. And it's a lot of extra capital expense. But lots of people have phones and tablets, and being able to go out in the field or on a factory floor and point it at something in a mixed reality kind of way. I think that's going to be actually the driver of seeing more 3D on mobile is going to be XR.
So is that getting ready to take you back in the direction that you were saying it was nice to get out of with all those Unix flavors, with all this mobile
Right.
and all these devices?
Right.
Is it going to get worse?
Right. Well, we do already support Android and iOS. I guess I didn't mention that earlier, but yes, we are going to see not only of the mobile devices, but of course the heads-up displays.
Right. Well, hopefully that's good news for you guys, right? I mean, lots of people would want to leave that kind of work to you. You guys enable a lot of industry, so hopefully it's good news.
True. Yeah, I think it is good news. I mean, the harder it is for someone to build cross-platform 3D, the better that is for us.
Yeah, I know in the past it was always every new platform that came up, we're like, okay, good.
Yeah,
That's,
exactly.
Additional value here. So additional work, additional value. As far as mobile goes, though, I mean, are you seeing, the cloud has been, up and coming for the last probably 10 years, but really grown a lot over the 5 years. Does that drive mobile usage? I mean, products like Onshape and cloud-based technologies?
Surprisingly, I don't really think the cloud itself has driven that. Yes, you can have actually more compute power on the server and just send images essentially down to a mobile device. And I suppose that when there's a reason to be carrying a mobile device and put 3D on it, the fact that the cloud infrastructure is there and you could do things like convert a 3D file in the cloud and send a viewable down to the device will indeed help it. But that's not what's holding it up is, I think, just demand for XR.
So it's the use cases. It's not that the technology's enabling it. It's more people aren't figuring out, well, what exactly would I do with it? If you could put 3D anywhere on glasses, in my hand, in a phone, whatever, what would I do with it? But and your thought is, well, once they figure it out, though, cloud might be part of the answer, but it's not going to drive it.
I think it certainly will be because the devices, although they're advancing pretty rapidly, they don't have a lot of memory. They have less compute power than a desktop, and a lot of the heavyweight CAD data just simply may not, the device may choke on it. So you still have to do a lot of work in the cloud and send a viewable down to the device.
Does that change some of what you guys have to do or how you do what you do? Or no, it's really not going to impact us. We're kind of playing on one side or the other, the mobile or the cloud.
Right. We do already play on both sides. So we have companies using us to build lightweight front ends, either in an installed app or to run in a browser. But we also have partners that use our 3D technology to convert on the cloud and also even to render on the cloud. You have a particularly lightweight device, you want to actually do the rendering on a server and push the images down. That can get expensive with using the GPU in the cloud, but it's doable.
So what are some use cases then? You mentioned XR. What are some use cases that you think would drive additional cloud usage?
I think the primary barrier, if we're talking about cloud in general and not necessarily cloud and mobile, is the steady comfort level that companies, enterprises are getting to in terms of security and realizing that any approach, cloud or otherwise, has security vulnerabilities. And as people get more and more comfortable with that, there's no question that the ability to have different usage models, different business models is better. The IT infrastructure that an enterprise needs to support is better. The ability to deploy faster is better. So as the comfort level keeps rising, and it is rising pretty rapidly around security, cloud will continue to be adopted.
That brings up a really interesting point that I heard something related to that last week. I was at a conference and they were talking about secure means of streaming 3D data to 3D printers. And it was in a defense context. But they were saying, look, safest way is not to have the data on the 3D printer, but to stream it to it as it needs it to do the printing. I thought, okay, interesting. It reminded me of something that came up years ago. I mean, this is, maybe even 20 years ago when I was working as an engineer, talking about protecting IP, even from just 3D viewers. They're like, oh, if I stream my data as WebGL, I could still grab the 3D and steal it somehow. And so how much do you guys play in that space in terms of the components you're offering and securing people's information, even with streaming? Can you talk a little bit about that?
Mm-hmm. Yeah, that's a good question. I mean, we're now going back more than 15 years, but Adobe acquired a company in the south of France who did data conversion. And the way that they did it was they would just actually spy on the OpenGL calls during a CATIA session, for example, or a Creo session, Pro Engineer at the time, and actually through that be able to determine what the 3D shape was. But all you really get is tessellated information, and most people feel completely comfortable that if all you have is the triangles representing my model, you don't really have much, and so the IP is still protected. So we don't worry about that too much. I mean, when we are doing our web platform is actually streaming a compressed format, which is would be hard for someone to reverse engineer. But once it's rendered, as you mentioned, in a browser with WebGL, someone could capture those calls, but I don't think it would gain them much.
Right. But to your point, it is sort of a benefit of the way you guys do what you do is, you wouldn't get much out of it if you tried to capture the information that way, but you are streaming just the lightweight. You are streaming just the visual and helping keep more of their IP safe by how you deliver the 3D that people see.
Yeah, true. Yeah, the important stuff is not going down the wire in the browser. But if you're so concerned about security that you wouldn't want someone taking a photograph of your thing, that's essentially
it would still
the same
be a problem.
thing. Mm-hmm.
Yep. But it's an important thing to think about just, as we zoom out and, we love having folks like yourself, experts in these areas on the podcast. But as we zoom out for the audience who's listening to this, thinking about all kinds of digitalization topics, that's a really important one, right? I mean, think about what are the components underlying whatever it is you're trying to do, and do they work with your data in a way that inherently keeps it safe, like you just described? Like, I'm only streaming the parts that people need to know or need to see, need to use, not everything.
Mm-hmm. Yeah, good point.
Yeah, because there was even an aspect of that in the way 3D translation happened. Is basically you always had the option of just getting the tessellated data. So if you wanted to send things to a supplier, you didn't have to send them the full BREP model. You could just send the tessellated information so that they could work with that.
Mm-hmm.
So again, other things that have changed aside from platforms is all of the hardware underneath. The graphic cards and the processing is expanded, et cetera. How has that impacted both what you deliver to your customers, your partners, or as much as what they are able to deliver to their customers?
Yeah, certainly graphics hardware has advanced significantly during that time, for sure. And in a few ways. Number one, just it's the raw power, the amount of stuff that you can draw, but the visual quality of the stuff that you can draw with current hardware. We used to hear all the time that engineers actually, they don't really care about how the quality of the rendering. They care about performance and precision. But I think actually what they're really saying there is that they care so much about performance and precision, they're not willing to make a trade-off for visual quality. But as the advances of hardware have gone forward, those trade-offs are becoming less and less. You can have your cake and eat it too. You can have strong performance and the visuals are improved. There are still trade-offs. There are still certain ways of rendering that if you wanted to go that route, it's going to cost you something in terms of time, or you're going to have to simplify the model such that it's less useful to an engineer. But no question that the hardware makes it better. I keep thinking that or I used to think, I've since given up thinking this, that at some point that trade-off will go away because the hardware will have advanced so much. But what we then find is that the more the hardware can handle, the more demanding the users are. They want bigger, more complex models. They want it to look even more realistic. So people find a way to fill up the capacity of the hardware the minute it arrives.
We used to joke about that in engineering. I have to see the threads. I have to model the threads, right?
Yeah, exactly.
So along those lines then, when we're talking about graphics and expectations, how closely related have 3D engineering graphics and gaming graphics? Because I remember at a point it was like, the 3D engineers or the engineers, they're more interested, like you said, in the underlying technology or the underlying detail, whereas gamers' visual quality was really important. How much are they coming together at that point?
They're closer than they've ever been, but they're not really all that close. So what you need to do in an engineering application with the detail, like Jonathan, you're joking about, I need the threads. I need all the details in the threads. I need all of that data maybe connected back to VREP data or some metadata. I have to carry a lot of stuff around to make that model intelligent. And because I want the user may need to do something very specific, it has to be highly, highly precise, which implies more and more triangles. What games and entertainment do is a series of the stuff looks great, but it's kind of stripped down. It's down to the minimum triangles they can get away with. They use images to make the stuff look really good. But if you try to zoom in and really do maybe a measurement on a piece of curvature, it would be useless. Or if you wanted to do finite element analysis, it would be useless. So they still are quite different. They're using different approaches, but I say that they're closer than ever before because you have really nice engines like Unity and Unreal that are starting to address more industrial use cases. Like there used to be times when someone would not consider using a game engine, but where now they would. And those situations are when that detail's not really so critical. So examples of those workflows, and we supply the CAD import to Unreal and Unity and others, is that they take that detailed CAD data that we provide them, simplify it down to a way that can work in their environment and sort of prep the data for their environment. And the use cases where that real world CAD data is useful are things like if I've laid out a factory floor and I want to simulate that floor and navigate through that floor, I don't need the threads on the screws as you're talking about. It just has to kind of look like the robots and kind of look like the machines on the floor. Or if I want to walk through a building. So we are starting to see more use cases that previously we would have put on the industrial side that a gaming engine is able to handle. And with that said, as the power of the hardware increases, we are, and other people developing graphics for engineering are adopting techniques that the gaming community has been using for a long time. And that's always been the case. They've always led the way and pushed the way on advances because, believe it or not, it's a hell of a lot bigger market than engineering software. Yeah.
Well, that makes perfect sense. I am surprised that it's always been that way. Because I think back to late 80s and early 90s, and I think, well, yeah, video games were cool, but I assumed that engineering was sort of more advanced in terms of graphics back then. But I certainly get the fact that it's been the two have been working on the problem from different angles for a while.
There might have been a day when they were the same. I'm not really sure. I know, like Pong was pretty basic. I'd say, but
that's exactly what came to my mind. Yeah. I feel like engineering was ahead at that point.
Engineering probably was ahead, even though it was wireframe.
Right.
But if you believe the idea that engineers don't care about visual quality, then we would still be using wireframe graphics, or we'd still be using flat shaded graphics in serious applications like SolidWorks and Solid Edge and Creo and those, but we're not.
I'm curious, are you seeing a greater expectation as younger users, younger engineers come on board? They've grown up with this technology. They've grown up with games in a way that we did not. We all just acknowledged, yes, we played Pong on our TVs. That was not high-end graphics. But these kids have come up with the expectation. Do they have higher expectations of their engineering applications as well, based on what they've seen growing up?
I think so, but I also think it's not incredibly new. It's probably 15 years now that game graphics have been well ahead of engineering, maybe even a little bit longer. And I know Carl Bass, when he was CEO at Autodesk, used to say that all the time. Like, why can't engineering graphics be the same? So sure, people coming into the workforce who've been gamers do expect more, but there's been gamers coming into the workforce for a long time, and they basically just get that beaten out of them. They pick up a piece of engineering software. They're disappointed at the gap compared to what they're used to. They ask somebody, an old person like myself, why is that? And they explain about the heavyweight data and everything, and then they sort of accept it. But that pressure is there. But that visual quality, everybody knows that the users would prefer more visual quality. So even though a CAD system, for example, is not competing against a game for graphics, they are competing against each other and creating more advanced graphics that the users is more like a new user is expecting, can be a source of competitive advantage. So that pressure is definitely there, but it's not new. It's been what's been driving things forward for a while.
So I want to ask a crystal ball question. Do you, when you think about the future, do you see any kind of unification of that? That like, oh yeah, we're going to have like one approach to rule them all that'll give us both the detail and the visual, and like one day Unity will be the best CAD kernel on the planet, that kind of thing?
Yeah, right. Unfortunately, I don't see let me roll my crystal ball. I don't really see that. I think that there's been a lot of efforts over the years to create some standards, like there was, OpenGL, free scene graph technologies. There was a project called Fahrenheit that Microsoft worked together with HP and others on to create the one graphics engine that will rule them all. And at the end of the day, every engine is optimized for something, and it tends to be optimized for the kind of data it expects. And so it's particularly good at rendering the kind of data it expects to get. And so far, I have not seen anything that doesn't create pretty unacceptable trade-offs for doing absolutely everything. Even it's challenging, companies like Dassault or Hexagon have a lot of have applications that do CAD, CAM, measurement, CAE. They even have mining applications, and they would all love to just have one graphics engine that they develop that is top tier in every single way and every single type of data that they might get, but there isn't such a thing.
Right.
You have to make some trade-offs.
Makes sense.
So moving away from graphics and into solid modeling, because I know that you guys have done a lot of work with solid modeling as well. Out of the direct modeling, parametric CAD, generative design, which do you feel had a greater impact?
Well, I would say parametric design by a mile, but I'd put a caveat on that and say so far. So parametric design was a remarkable breakthrough with its ability to, using boundary representation, to represent shapes that were very hard to represent before, and to offer a level of precision that was very difficult to achieve before. And then a whole industry reacted to that, so that every software in your chain, from design, analysis, machining, etc., mold making, was all assuming, it was expecting BREP data. So the parametric element was important, but even more important was the fact that it was based on this boundary representation model. So that was a huge sea change. Direct modeling was more of a step change. It's certainly more convenient to model, and especially to change a model using direct modeling, but it's still using BREP. So for that, I think it's a useful tool and a useful way to model, but not a revolution. Generative design is interesting because whenever someone says generative design, I think most people think about these really crazy, lattice shapes that can be developed that would be impossible to machine any other way other than on additive. But the generative part is just saying, I'm going to send some parameters to the computer and let it do what it wants to do. And there have been tools for doing things like generative design, but one of the constraints that you give the compute power is that it needs to be something that fits these criteria so that it can be created using subtractive manufacturing and not additive. So the word generative doesn't necessarily imply those crazy lattices. But what is really cool is the amazing things that it can create, which are difficult or impossible to model with BREP or to move around. They're just way too heavyweight. Systems choke on them. So I think true generative, like unconstrained, make whatever shape you want, is going to rise in lockstep with the adoption of additive, and they're going to support each other because people are going to want to make these more lightweight and interesting designs that are perfect for this criteria. But to do that, they're going to need additive manufacturing, and the demand for each will drive a circle of demand, I think.
So I'm going to back you up on that one, Ron, for a second, just to make sure I tracked it right. I think what I understood you say is, hey, when you do generative, the calculations it comes up with, those could be hard to make. And we have to make them with additive now because they weren't even useful to make when we didn't have additive manufacturing. If you had to machine it, it was like, what's the point in even representing that? But you just brought up an interesting point, I think, which is, well, then there's also just, can the solid model represent it? So there's two steps there, right? There's like the computer could calculate it and tell you ought to have this crazy looking organic or lattice shape. But all right, can I represent it in a model? Number one. And then number two, could I print it afterwards? So they both are an issue, right?
Yeah, both are an issue. It can make crazy things. That's true. It can design crazy things that can't even be printed on a 3D printer.
Right.
But I believe that, it doesn't necessarily imply, generative does not imply that it has to be 3D printed. I think if you if a smart engineer is feeding a system a set of parameters that says, I need a design that fits within this space and that actually is with this much tolerance or this much ability to withstand weight and is made of these materials and actually could be represented by BREP, it can drive a BREP engine. The computer can drive a BREP engine and only design things that are capable of being created using subtractive.
Right. It's just yet another constraint, right? So like, hey, it needs to be modelable, it needs to be machinable instead of printable. And yeah, so it's just, that's extra constraints when you're being generative.
Just another constraint. Yeah, exactly.
I also want to go back to what we were talking about with the different types of modeling for a minute, and you'll forgive me, it's been a bit since I've driven CAD. So direct modeling, parametric modeling. I remember doing parametric modeling and putting in all my parameters and calculations and things like that. But direct modeling, is that the sort of push-pull, move this hole over there? Or is that...
Yes, exactly.
Okay.
Exactly. So the parametric modeling requires the designer to almost know in advance how they're going to construct and build the thing that they're trying to design. And they have to very prescriptively tell it, insert a chamfer here, insert a hole here, and to know that these things are connected and that one change impacts another. Or direct modeling, it's much more intuitive for the designer.
Am I remembering the right term? So parametric is the history-based modeling, whereas direct modeling is history-free because you can that dependency doesn't exist?
Yes. Mm-hmm.
Right. Okay. All right, so I did remember that.
Yeah, good. Now we've actually hit the limit of everything I know about modeling as well. So yeah, we have to be careful.
But it's interesting, just in the context of, the podcast, the audience, again, that we hope is listening and interested in what we're talking about, makes a big difference, right? Because parametric modeling it's great for engineers. Engineers think that way. Lots of other folks need to deal with products. And that's where direct modeling was such a huge thing. Like, wait a minute, if I understand 3D and you teach me a few things about this interface, I can have something to say about our products. And I don't have to understand all that history and the calculations and, first you do this operation, then you do that operation. No, just move the hole where you want it and explain it to me in 3D.
Exactly.
Well, and it's particularly good for conceptual modeling, exactly what you're talking about. And then you can pass it to engineering and say, hey, can you make it something that looks like this in parametric CAD so that I can drive it? So I guess, but what you're saying, Ron, is if it doesn't imply generative, or generative doesn't imply additive manufacturing, but it will drive it at some point. I mean, it does, additive, it doesn't really require generative either, but I would assume that you would expect that they will both continue to move forward for an undefined period of time.
For sure.
Because, additive is not going to replace subtractive manufacturing anytime soon.
Not anytime soon, no. The industry is so built up around subtractive, and so much of the software is built around that, and so much investment from manufacturing companies have been put into that approach. I was at the Formnext show in November in Germany. It's pretty clear that there's still plenty of investment going into additive. And depending who you talk to, some people are disappointed about the adoption of additive, but I think the only people who are really disappointed are maybe investors who they thought that it would come around, that there'd be this hockey stick, it would come around much quicker. Maybe they haven't spent a lot of time around manufacturing. These things change very slowly, but what one can do with additive now and the materials science advances is remarkable. So I'm pretty bad at predicting what's going to happen when. I always think it's going to be a lot faster, but I can say with confidence that 5 years from now, there'll be more things that are created with additive than they are now as a percentage of all things made. And 10 years from now, it'll be even greater. I can say that vague sentence with a huge amount of confidence.
There's no doubt. I mean, it's just what it's able to do with providing stronger and more lightweight. Aerospace, I know, is a huge adopter and probably the greatest value that you can get there.
One other point about additive and subtractive, I think that part of the challenge is that we've gotten our processes with subtractive to the point that it's really, really consistent. Like you can actually produce parts extremely consistently with a subtractive process. It's less consistent with 3D printing. It just hasn't been refined and beaten on there. So that's the reason why if someone needs to make 10,000 of something, they're happy to press the button in their factory to do it in a subtractive kind of way, but that would make them pretty nervous in a additive kind of way. So they're using things for smaller batches. It takes a little more time to verify that this is actually within the parameters of the design, et cetera. But these things will get there.
Yeah, I think you're right. And not only the conditions that all of those products are being produced in, but it's also the types of additive you're talking about. Mm-hmm. Because there's a lot of, if you go from manufacturer to manufacturer, from HP to desktop to, Stratasys, et cetera, they're all using different processes too. And it'll determine to shake out like, okay, what was the best process for doing that?
Right. Can you imagine the way it is with parametric CAD and BREP? The designer is not thinking for a second about how's this going to get manufactured and which CNC machine is this going to be used on. They don't think about that at all. But in additive, you almost do have to say, okay, what specific materials, of course, but also what machine is this going to be created on? Because there's variance in their capabilities, how much deformation to expect, et cetera.
Yeah, I think that's absolutely right. And I'm very curious to see what the future holds for engineering in that respect, because to your point, you have to think about how you're going to make it to use or to get the most benefit out of some of these exotic manufacturing mechanisms. And we first saw this, I think, maybe not first. We saw this previously with composites, right? It was worst way to make a composite is, design it in aluminum and then go make that same thing in composite. No, not a great idea. Think about, well, what am I making? What are the unique possibilities or capabilities? And then design your part based on that. And I think additive is the same thing. All right, what can the machine make? What can it do? What's the material I'm using? Now, what I wonder about is, what does that mean for engineers, right? I mean, for some engineers, me included, it was hard enough to think about the part I wanted to make, much less how it was going to get made and factor then that extra constraint. But it's interesting.
Design for manufacturing is a big push, and it's for that reason is try to make it so that there's as much knowledge as possible way early in the process about that. It's just harder with additive because of the variety of different machines and how they are expected to behave.
Just more
materials, endless materials. Yeah.
Mm-hmm.
What I'm curious from your perspective and TechSoft's perspective, what have you guys had to do or needed to do or been able to do that's new with additive that folks have asked you like, hey, we need this in terms of what you're offering us because of that? Is there anything there that you could talk about?
Yeah, sure. We do everything we're doing on the visualization side. That's the same. Everything we do with meshing and solving, that's the same. Everything we do with CAD translation, that's the same. But we do provide CAD import to most of the companies making 3D printers and making software for those 3D printers. But there was a gap there where there's you might convert a model, you get something out of a CAD system, you convert it, but it might actually have some subtle problems or some significant problems that make it unprintable. So we didn't really have an answer for that. We ended up creating a partnership with a company called MachineWorks and a kernel called Polygonica. Actually, Jen was pretty involved in making that happen, so that Polygonica can actually take this translated CAD file and make sure it's printable by closing gaps, taking care of sliver faces, and really preparing the model for printing. So that's something we never really had to do before, but without it, there was a gap missing, and we're standing there looking at our partner saying, we don't know, we don't really do that. And the partner saying, we don't know how to do it either. We thought you...
Right.
And thankfully, we have this partnership with Polygonica that's working out great.
That is cool.
And solid modeling has changed a little bit as well to represent that, right? I mean, you've got convergent modeling within Parasolid, and I think ASUS has something similar to be able to represent those to both a BREP model and a... How would you go?
Yeah, true. That you can combine them in the same scene. We were talking earlier about parametric and direct, or really BREP versus triangle-based, mesh-based, which is what most of these generative design are using. And there's this data discontinuity. So, okay, I've got, let's say I'm using some really great, I'm using N topology. I've designed something super great. You know, it's pretty hard then to take that interesting model and move it into different software, because that software is expecting BREP and it needs to operate on BREP. So this data discontinuity creates these gaps in the workflow for an engineer. Says, I don't know, I just designed this thing and I want to be able to do X, Y, and Z with it. But depending which other software they're using, that might be easy, or it might be hard, or it might be impossible. And things like convergent modeling from Parasolid and what the combination of ASUS and CGM can do is mix those modes at least. They can't go from one to the other. Well, they can go from BREP to mesh. They can't go mesh to BREP, but they can at least put the two things in the same scene and perform modeling operations. And so that chips away at that discontinuity. It chips away at the hurdles that an engineer would have trying to move data from one application to another.
So I'm gonna dumb it down for myself for a second. So this is effectively different mathematical models of the 3D, right? That's what we're talking about when you say convergent modeling. And so one type of calculation, or something that a computer might do to help out an engineer in designing it, might yield or need one kind of mathematical model, but a different operation might need a different one. And that's your point about convergent, is that's starting to let you move more easily across those models.
Yeah, I think that's exactly right. And one description or one workflow that may describe it very well is if you are trying to design a custom prosthetic, or let's say a knee replacement to fit exactly this person's knee. That actually metal knee that's getting designed is getting designed with parametric data, with BREP data that's hyper precise. But you also then have the human body is not that precise. So you may have gotten the rest of it through scan, which you then turn into a mesh. And so you need you need the mesh information so that you're designing that knee to fit perfectly in there. And so that's what that convergent modeling is able to do, is to say I can take both of these ways to represent a 3D object and use them together.
Gotcha. So is it, I'm going to ask a question, might have this wrong, but so is it like the difference between, I could have mathematical models and equations of curves and lines, and that's kind of your BREP view of things. But then if I really scanned millions and millions of points and had a point cloud, that's my other view of things. And it's like, well, to use those two together, that's where convergent modeling is. Is that what we're talking about?
Exactly. Mm-hmm.
Okay.
Mm-hmm. Yeah.
You got it.
That's great. I mean, I think this is such a good topic for for what we're talking about in general, because it's easy to think of, oh, 3D models are 3D models, right? It's all the same stuff, but there's so much work that has to go on behind the scenes to use those models for different purposes. And like you mentioned, to start to shrink the discontinuity from using a model for one purpose to another, to another, to another, to where it's sort of universal, whether it's, graphics versus precision in the model, like we talked about with gaming earlier, or whether it's this case we're talking about. It's not 3D is 3D is 3D. I mean, I'm saying that, like, you no doubt know that, but I think it's great for us to expose that to people because it's easy to oversimplify it.
Right. Yeah. It looks the same when you see it on the screen, maybe, but there's a lot behind the scenes that's different.
So as we're continuing to progress our ability to create and reuse digital data, whether it's graphical or engineering data, how have you seen the role of standards change? Are they still relevant, in fact?
I think they are relevant. I have a love-hate relationship with standards, like a lot of people. It's like there's variations on a standard. There's how someone implements a standard that can break what its promise. But I think in the manufacturing world, STEP is actually a pretty good success story, a slow-moving success story, but a success story. It's taken a super long time. Everyone knows that the native formats are more information-rich than a STEP file, but yet STEP is a pretty useful lingua franca between applications, and we're now at the point where most people have implemented the standard AP242 pretty consistently so that you can use it to move between applications. Would you prefer to use that native SolidWorks file or that Creo file or that CATIA file? Sure, but that's sometimes, in most work environments, not realistic. So definitely there are success stories out there. STEP is one. IFC is becoming one as well in the building industry. They're definitely useful. They're just slow moving and always behind the state of the art. But I don't know that there's a way around that trade-off.
The one I always love to hear the debate of, and this happens at a couple of different conferences I go to, is somebody will inevitably say something about, STEP or this standard, that standard. Oh, it's a bad standard. Somebody else will stand up and say, well, is it really the standard that's bad, or is it some software provider's impletation of that standard? It's always a back and forth debate, right?
Right. And you'll never settle that. And but I do think it's useful. And I think that as we were talking earlier about the rise of the cloud, that's really so much about the data model and where the data lives. And then you have these applications. They might be in a browser, they might be an installed application, but cloud applications are made powerful by the fact that the data lives somewhere else. I could lose my laptop, and it used to be a disaster. Now, as soon as I could get to an Apple store and connect to iCloud, I'm back up and running with everything installed. So it's really the data there. And you see things like Autodesk Platform Services, CATIA V6 is this same model, where files become less and less important. And there's just one live data model that through an API people are connecting to. And so STEP is a very useful file format to transfer. So are all the native files to transfer. But what will it mean when everyone really fully gets in their head about moving away from file-based to a live database? And what format do we need then?
That's an interesting point you bring up, Ron, about, I'll say my take on it is portability, right? Is some of what I hear you talking about. And STEP and standards for data is one piece of portability, right? And what you just mentioned about the cloud is another piece. It's ubiquitous. Oh, can it be replicated everywhere? Can I get to it anywhere? But all these are such interesting pieces of getting us to that point where we don't have to think about it. That's what we're after, is I don't have to think about it. I can go get at my data and work with my data wherever it is, whenever I want, however I want, that kind of thing. And going back to what we talked about with direct modeling earlier, I think that was a big step, no pun intended, but that you could take a model that doesn't have its intelligence and you can now still operate with it, right? I mean, I remember back in IGES days, right? It was like, oh, hey, you got this model. What are you going to do with that? Nothing until you try and pull it in and reinterpret it and all that sort of thing.
Yeah.
But we are getting to that point where the standards are a piece of that portability picture.
Right. Yeah, you're not thinking about it. Yeah, you're not That's exactly it. You're not thinking about what format is this in. Yeah.
What are we missing with standards? Where do they need to go and take us? I mean, what do you see there?
Well, I mentioned earlier my love-hate relationship with them. I know they can be useful for what they're useful for, and I'm careful not to hope for too much. But STEP, as another example, continues to advance, and it will continue to advance. So, as I mentioned, the lingua franca, it's the basic level of being able to communicate. But that basic level, with each iteration of STEP, has continued to grow. So it will continue to allow us to do more and more, even if we're not dealing with the native formats. But the native formats keep advancing too. So there will always be this gap between what the standard can do and what native can do. I'm not seeing a world where everything is really run by a standard and there's not native formats, but don't see a world where we don't need standards and that just goes away.
Yeah, and the real challenge is that it's something proprietary can move much quicker than a standard because it requires only the organization, the vendor, to agree on how it's going to move versus all of the vendors or all of the implementers to agree. But the other thing that's nice about standards, and STEP in particular, is that we talked earlier about IP, and because it's providing that basic language understanding, it's a way to protect IP. So you get the data to recreate the objects, but not necessarily all of the intelligence that would be in a proprietary CAD system.
Yeah, for sure. It is more protected because it's more limited in what's in there. Mm-hmm. It's enough that a supplier who has to manufacture something can take that STEP file and really have everything they need to know in order to do their job. But can't necessarily recreate all the features and the design intent behind it.
So over the last 25, 30 years, you've seen a lot of changes in the engineering software space. What do you think has had the largest impact? Or what has surprised you the most? Either that it happened or that it didn't happen.
Let's see. There's friends I don't want to upset, but no, I think I have. Well, I mean, it sounds crazy, but the biggest change is actually the ubiquity of the internet. It seems silly to even mention because it's so ubiquitous, but when TechSoft started in 1996, that was still the early days of the internet. Even then, of course, we could see and everyone could see, hey, this is going to be huge, and it has been huge. But that aside, my biggest surprises are actually how long most changes have taken. When we first created our web platform in the end of 2011, and we thought 5 years, basically, everything's going to be cloud-based software. The desktop is dead. We were wrong about that, like we've been wrong about a lot of things. That transition's been much, much slower. And in fact, the death of the desktop has been greatly exaggerated. Adoption of additive manufacturing has also been slower than I would have guessed. And I'm surprised that it's taken so long for AR and VR to take hold. It still hasn't really crossed the chasm in any way. But my biggest surprise is actually that we have not found another way that we can all agree on to model things beyond BREP. It shows you how good BREP is at designing something that takes all ambiguity out of the geometry, at least the shape. Like it's extremely accurate, and everyone can see exactly how the tolerance, etc. But it's surprising that that's been the way people have been doing it for more than 30 years, close to 35 years, and that we haven't found a better way is surprising. Not that I think there's anything wrong with BREP. I just think that there have been a lot of advances in geometry. There's different ways to model, implicit modeling, a lot of the way the generative design engines work, but they've not been able to displace the old warhorse of BREP.
Yeah, I mean, it really is surprising if you think of all of the advances we've had, and yet that hasn't really changed. And maybe it's because it's a mathematic model.
Maybe it's just that good. Yeah.
Maybe it's just that good.
Yeah.
I can tell what's going to happen after we record this podcast episode is somewhere in the middle of the night, I'm going to wake up and be like, oh, I should have asked Ron that.
Well, you always feel free to send me an email and I'll get someone that knows the answer to respond.
No, these are like some of the things you're bringing up are good, deep thoughts. I mean, Yeah, I'm so glad we've had you on because these are really interesting points.
My pleasure.
I think, matter of fact, Jonathan, one of the questions that you did want to ask, because this was one of the ones that you had put on there, is, over the years, and actually in the last 5 or 6 years, TechSoft has acquired a lot of different component technologies, expanding your areas in graphics visualization, particularly. What are some other lesser known types of technology components or providers like TechSoft, but like in different areas? Are there any?
Yeah, that's a good question. Well, if there are, we would certainly love to add them to our portfolio. We want to be able to say yes to anything that someone might need when they're developing really serious engineering software and they say, we need this or we're looking for that. We'd love to be able to say, we can help you with that. We know that that's not possible, which is why we have a lot of partners, like I mentioned, Polygonica, who can fill in some of those. There are interesting things in adjacent markets and even within engineering that are, I think, lesser known SDKs in the geospatial area. There's a graphics technology from a company called Cesium, which I think is a great example of what I was talking about earlier. Is that a graphics engine purpose built for something is going to be great at that thing, and that's an example of that. We can do that kind of stuff too, but not as well because we don't specialize on geospatial data. So it's very specific to that market. There's a physics engine out of Sweden, a company called Algorix, that is really pretty remarkable in terms of what it can model, the real world physics. I think that's an interesting area. We are seeing more and more companies actually, IoT and digital twin is an important area. And there's lots of companies that are talking about their IoT platforms or IoT SDKs. They haven't really settled on the vernacular of what's what. But IoT is an interesting area in that, is that a development tool or is that a tool for an end user? Because if you go into Honda or anyone, you have to deploy that system custom to the machines that they have, to the workflows that they want. And so there's quite a few of those IoT platforms out there. And we sometimes see them getting used with like charting SDKs. Like there's a company called Lightning Chart in Scandinavia that has a really good tool for absorbing lots of data through IoT and actually rendering it in a way that makes sense beyond just charts and graphs. So yeah, there are things out there that we see. Verific is a company in the EDA space that really helps application developers consume data about their EDA designs and verify that it's designable and workable. I will say this I mentioned IoT. I'll say this about the world of SDKs. We used to believe that there was this hard line between this product is a toolkit for developers. This is for developers. And this product is for end users. And I think that line continues to get blurry. I mentioned IoT platforms as an example. I see applications that are clearly made for end users, but they have a Python wrapper and can be run headless and fit into a workflow that a developer is creating. So is that a developer tool or is that an end user product? It's not always so clear, and that's particularly true as we move to the cloud. Let's say I'm doing something, converting a CAD file and preparing it for 3D printing, and I have a service, and I charge for that service. I don't really care if the person who's hitting that service and paying me some money is an individual user with one file that they have to print, or an enterprise that wants to do this in a huge volume, or a developer who has created some solution that needs to use my service from time to time and they pay me. So is that a developer tool or is that a product for an end user? The lines are a lot blurry than they used to be.
Why do you think that is? Is it because of the rise of the citizen developer or is there something else that's making that blurry?
That's a good way to put it. Yeah. Well, the cloud platform makes that one thing available to just say, I'm not licensing anything. I'm just using what you do well.
Right.
And I'm paying you for it. So you don't care who's, the line is irrelevant. But yeah, I would say the citizen engineer is part of that, is that people are certainly capable of, there's a lot of people who are capable of writing Python scripts There's a lot of no code and low code movement where is it actually, are you a developer or are you just configuring something? And who cares about those semantics? I'm making this piece of technology do what I need to do to address my workflow.
You brought up a really important point as you were describing that, though, and that's about now it's a usage model and not always a licensing model, right? So moving away from the do I have to think about myself as a developer and I'm putting together a solution and there's steps to that? And no, I don't care. I'm just going to use something, right? It's
exactly
service-oriented architecture, right?
Yeah,
I use it as a service. It's just what I need and I make it happen. And whether I'm a developer or I'm a user, it doesn't matter.
Right, exactly.
That might be the biggest impact of the cloud that we've talked about, is that change in mindset, enabling that change in mindset.
Right. I don't have to have it all. I can actually jump out and call microservices for all manner of little things I might need to do. Mm-hmm.
Okay, well, I want to be cognizant of time. I know that we are way over on our usual podcast. That's not a bad thing necessarily. I think it's been a very good conversation.
This has been awesome.
Yeah.
Great. It's been fun.
Yeah, a little bit of a look back and then a tiny bit of looking forward as well. So, Ron, I want to thank you for joining us today.
My pleasure. Thanks for having me.
No problem. And if anybody wants to, I just want to encourage our listeners, if you have any additional questions, either for Jonathan or I or for Ron, we keep in touch. Please send them on over. If there's something on the podcast that we haven't talked about that you want to hear us talk about, let us know. Be part of the conversation. And until next time, stay sharp.
Thank you for listening to this episode of Stay Sharp with Razorleaf. We wish you and your family happy holidays as this year comes to a close. If you have any questions or comments for our podcast team, or have an idea for a new topic for our team to cover in 2024, please send an email to podcast@razorleaf.com. We would love to hear from you. Until next time, stay sharp.